Good afternoon, ladies and gentlemen. I'm glad to have the chance to introduce my research work. I'm a first-wide micromagnetic sensor for OSI magnetic field mapping. I'm from Hero Technology Group Company Limited. There are many places where weak magnetic signals need to be measured precisely, including geological exploration, environmental monitoring, biomedical geomagnetic disturbance, industrial earthquake, and warning. Magnetic field mapping, as one of continued paired technologies, plays a vital role for on-site inspection. Looking back into the recent science and technology development history, magnetic sensing have been under decades of development. This work would propose a high-performance magnetic sensor based on the giant magnetoimpedance effect of special magnetic materials. Compared with current magnetic sensors, such as GMR magnetic resistance sensors, flux meters, and Hall sensors, our first-wide magnetic sensor has comprehensive technical advantages, such as high response speed, high sensitivity, high resolution, wide measurement range, low power consumption, and small size. A prototype UAV-based magnetic field mapping equipment has been developed. Field experiments have been carried out to demonstrate its potential application to the OSI of CTBT. Our objectives is to design amorphous alloy wire weak magnetic sensor probe and to study the matched processed circuit and develop a special high precision sensor. The amorphous alloy wire is the key material of sensor. The material is a kind of core based of coffee symbol and amorphous alloy wire. The special characteristics of the material is the giant magnetoimpedance effect, namely the phenomenon that the AC impedance of magnetic materials changes significantly with the change of external magnetic field. The electromagnetic properties of amorphous wires are mainly evaluated by the following parameters. The first is giant magnetoimpedance effect, such as rate of change of impedance. The second, hysteresis loop parameters, such as correctional force, residual magnetism. The third is anisotropic permeability. The preparation of high-quality, continuous, and uniform amorphous fibers places extremely high demands on the process level of the equipment. For example, preparation principle of the inner wall spinning method and preparation principle of the glass coated drawing method. Due to the amorphous characteristics of the amorphous fiber itself, the material is prone to structural relaxation or crystallization phenomenon when the temperature is high. At the same time, natural residual stress is generally introduced due to the actual high cooling rate during the preparation of the amorphous fiber. We must remove the glass coated on the amorphous wire before heat treatment to maintain long-term stability of performance during end use. We can choose the chemical or mechanical treatment method. When the glass layer is removed, the magnetic elastic energy is less than the static magnetic and exchange energy due to the partial release of internal stress. So the internal magnetic domains transfer from radial distribution to axial distribution. The amorphous wire generally needs to be heat treated before it is used as a sensitive material. The purpose of heat treatment is to form a part of the nanocrystalline phase in the amorphous phase of the material so as to obtain an excellent soft magnetic composite structure of amorphous or nanocrystalline. We can choose one of the heat treatments such as direct current annealing, Joule annealing, stress annealing, and electromagnetic annealing. After heat treatment, we must analyze the performance of the amorphous wires, such as impedance radio test of amorphous wire, hysteresis loop test, and axial hysteresis loop test, and magnetostrictive coefficient test. The phenomenon wave probe is one of the key factors for the micromagnetic sensor to achieve the designed performance. The basic components of the amorphous wire probe are amorphous wire, induction coil, bias coil. The following aspects determine the performance of the amorphous wire probe. First, core-based amorphous alloy is used, which has high material sensitivity due to its axial anisotropy. Second, the driving mode of the probe. The third is the diameter and the length of amorphous wire. The fourth is diameter and number of turns of induction coil and the bias coil. They are all amorphous wire probes with different lengths and different turns of coil. Under the action of high-frequency exciting current, when there is weak magnetic field or a slight change of magnetic field outside, the anisotropic magnetic domains inside the amorphous wire are deflected, and the direction of the magnetic domains is unified to the easy magnetization direction axis, and the impedance of the amorphous wire changes. Based on the working principle of the amorphous wire magnetic sensor, a higher frequency signal is needed to excite the amorphous wire. The excitation of sharp nasal parts is used, which has strong harmonic signals, and the amorphous wire is more sensitive to the frequency response of high-order harmonics, which can improve the sensitivity of the sensor. The coil collects the signal of the changing amorphous wire. The signal then is amplified by using an amplifying circuit, and this signal is integrated by using an integrating circuit, and a feedback circuit is used to generate a reverse magnetic field to achieve magnetic equilibrium with the external magnetic field. The stable voltage signal after magnetic equilibrium is filtered by a low-pass filter, and the output result is obtained. They are the amorphous wire weak magnetic sensor index. We can see these parameters such as measurement range, sensitivity, non-linearity rate, and so on. This is a comparison of the performance of various magnetic sensors, such as Hall sensor, AMR sensor, JMR sensor, fluxgate, TMR sensor, and RGMI sensor. We can see probe size, resolution, response speed, convolution, working rate, sensitivity, and working temperature. Our GMI sensor has comprehensive advantages. we can make handheld magnetic detection system. Using this system, we can find the target buried at a depth of 2 to 5 meters. This is our UAV-based target magnetic exploration system. It consists of the following five parts: UAV data acquisition module, GMI sensor, bracket, and software processing system. We must use system magnetic field composition algorithm. Using the algorithm, the overall measurement accuracy of the entire area is approximately 4.1 knot. Using UAV-based target magnetic exploration system based on the GMI magnetic sensor array, the ferromagnetic array area can be detected. So we can conclude our work would propose a high-performance magnetic sensor based on the giant magnetoimpedance effect of special magnetism materials, compared with current magnetic sensors such as GMI, TMR, flux meters, and so on. Our GMI amorphous Y magnetic sensor has comprehensive technical advantages. Thank you.
Thank you very much. Thank you very much. I think we have time for one question, if anybody would like to propose a question right now. And do you want to come to the microphone, please? Thank you.
Thank you for your presentation. Have you taken into account the presence of the drone? Because the drone, there is a motor, a brushless motor with permanent magnets, the influence, the measurements.
Oh, please.
Okay.
他就说是那个考虑到无人机这个磁场对你这个磁传感器的影响。
Okay, I can explain. When we use the sensor on the unstable platform, for example, UAV, we must use a method. The method is comparison method. Using the comparison method, we can reduce the influence of the UAV.
Okay, thank you. And I thought I saw one more hand going up there. Yes, one more question, one quick question. Thank you.
Thank you, Mr. Chairman. Thank you for a very interesting and detailed report. It's an achievement. My question is very simple. You indicated the temperature range of operating of this amorphous magnetic sensor up to 125 centigrade. Does it mean that's maybe for any other applications? Because I could not expect such a high temperature in case of operation of OSI. You understand? The upper limit of temperatures, 125 centigrade. This is a question.
I see.
So the
Underground. Oh, okay. Underground nuclear experiments can cause changes in the magnetic field of geological structures. When these magnetic field changes are transmitted to the surface, there will be variants of several nonce. By using highly sensitivity sensors, such as those with a resolution of 0.01 knot, such weak changes can be detected. Then, by placing sensors to form the spatial array, such as a line pattern, rectangle pattern, cube pattern, and so on, Combining with the owner deconvolution equation, the position where the changes can be inversely calculated, and the position error accuracy is about at the meter level.
Thank you. I think would be a good after this session. Maybe you can pick up the question regarding the operational range of the device as well. But go, Jilling. Thank you very much for your talk. Thank you very much indeed. So next we can move on to resonance seismometry, and thank you.